In the last video, we talked about the Doppler effect, and we even talked about what would happen if something was moving a pretty large percentage of the speed of light. And we said, okay, the color of the light would change. That's not too hard to understand. What if we examine a person on that asteroid that's moving at closer and closer and closer to the speed of light? What's different about what we see? Well, the person on the asteroid, I propose, is going to be using a yo yo. And that yo yo is going to go up and down according to the time scale that's on that asteroid. And we're going to sit stationary, and that yo-yo over there on that asteroid is going to be going up and down according to the time that's over there. And for us, we've got this super microscope, well, not microscope, this super telescope that will see that yo-yo and will see what's going on with that yo-yo and compare it to a clock that we have in our stationary position. Before we get to that, let's do the easy part. Let's do a comparison of a single dimension. That single dimension will be an x value. If you remember from math or don't remember from math, there's going to be a y-axis and there's going to be an x-axis. And on that asteroid that's moving close to the speed of sound toward us, there's going to be its own x-axis, we'll call it x asteroid, and y asteroid. Now, since the thing is only moving in one dimension toward us, the x dimension, then we can say that the y dimension on our stationary object and the y dimension on the asteroid, those things are going to match up. But the x dimension isn't. The x dimension, as the stationary observer sees it, that x dimension is changing with time because it's coming toward us. So I'm going to go look at a little picture and we're going to talk about that and try to do some math with just that easy part. All right, then. Here's the picture. I painted this character in red because, as far as we're concerned, he's not moving anywhere. He's stopped. He's stopped in one place. This one I painted in green because he's moving. And here's his yo-yo. Boop, 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 going up and down. That's what the little arrow's here. And then just to remind us, that's a yo-yo. Now, for the times, I put the question mark and the question mark because according to my title, it says time's not a constant. And that's the real question here. What's going on? I put the velocity of this asteroid in black because that's what this observer sees. This observer doesn't think he's moving at all, but we know he's moving. That's why he's in green. And also I put the velocity equals the change of x over a specified time divided by time. In other words, let's think of it as meters per second, if that helps you think about that a little bit better. And let's see, as far as this x is concerned, the x is not changing because he didn't think he's going anywhere. The asteroid, he doesn't feel any motion or anything like that. So how do we express the what we see as the green x in terms of what the stationary person sees? Okay, let's see if we can make this all work out. Let's make that green. The green x equals, and I'm going to change that to black. So hopefully this all makes sense. Equals v. Oh, one minor mistake here. it equals the green x equals the green x equals x minus vt. Let's see if that's enough to absorb now. The green x, as far as x is concerned, in other words, just say where this guy is not standing still with respect to time. It's going x minus vt. So let's say that's x, let's say many millions of miles away. He's moving, and he's moving closer. So his x coordinate, as far as x is concerned, is getting closer and closer and closer. So, what's the big deal? What's relativity got to do with anything? This doesn't seem very complicated. We multiply velocity times time, that gives us a distance, and that'll be the difference distance between what the person sees. You've got the green person that's moving, you've got the red person that's stopped. So, aren't we done? What about the velocity of light? Does the velocity of light differ between the moving person and the stationary person? If it does, if the velocity of light changes, then we're done. But what if the velocity of light does not change and everything we see, velocity of light, and everything the the green person sees is velocity of light, and they're the same? We gotta have something change about all this. That's what relativity is about. Is the speed of light is the same for all observers. If that's not true, then we don't have relativity. But if it is true, then we have to change the equations. That's what's coming up. Okay, since we looked at this picture, I've changed some stuff. I've added some fun stuff to this so we can make some sense of it. Now, here is the stationary observer who we think is the God of Almighty. It's this guy knows everything and he never changes, but that's not actually true because it's all relative to who's standing there. Anyway, here's the guy that's stationary. He sees the x variable in terms of his black coordinate system, x minus vt. So it's definitely moving with time. X, according to this guy, is not changing at all. So let's see what goes on next. What about the observer here? What does he see? He sees the x, according to this thing, as in his terms, x plus vt. So he sees it moving this way. He thinks this person is moving in this direction. So it's actually the velocity going in the opposite direction. So it will be going in the positive direction of his x-axis. So here's two viewpoints. Now, I'm going to introduce, let me cover this. See if you agree with this. The velocity going this way is the same as the velocity going that way. Well, at least the magnitude of it. The direction of it's different, but the velocity itself has to be the same. You agree with that? Yeah, you're going towards something, it's going towards you. The velocity is the same between the two. So I'm just going to correct that so we don't have to worry about that being different. Now, the x's are different, definitely. This x over here and this x over here, they're definitely different. So, what else am I going to talk about? Well, I've got these flashlights here. I've got a flashlight here that's shining a light toward Mr. Redman, and I've got a flashlight here that's shining a light towards Mr. Greenman. Now, are these velocities the same? Even though this one's going this way and this one's going that way, Are those velocities the same? Well, the velocity of light, depending on any observer, should be the same. So that velocity of light should be the same between these. And this is going to cause some very interesting differences between these things. Okay, things are changing a little bit here. Let's look at the what the red man saw as the green man's x. The green man's x was the original starting point as far as x was concerned minus vt. So that meant that it was moving to the left on our other diagram, moving negative. Negative is left. And here's the perspective of the green man, says that the red x is equal to the starting point, actually in the negative region, plus vt. Now notice what's important to know is that the t's are the same, and up till now we've just concerned that, well, t is t. It doesn't change one way or the other. Green t and red t, they're all the same. That sounds like we've got a tea party. Anyway, this is the other thing to look at. If we say that the t's are different, then I'm going to say that x has to be equal to some constant times the red t, the red x minus v times the red t. So that doesn't look any different than this one. But the red x from the other perspective, where you're only dealing with green variables, here's this constant and x plus vt. So this is a new idea that there's a t in there. So each one of these constants has to be able to relate one to the other, because they're essentially should be equivalent from either side of this viewpoint. So we're looking at both the green, this is the red viewpoint of the green x. This is the green man's, I'm sorry, this is the red man's view. It gets confusing, doesn't it? The red man's view of the green x, and this is the green man's view of the red x, how that's changing all the time. Each one thinks that they're stationary, but let's see what kind of constant we can come up with. And this is a really critical point, very critical. So let me point that out somehow. And this k is the critical point. Now, try to absorb that a little bit and notice the greens and the reds, how they've kind of switched around. The key point is that the t's are different here. We've got a green t and a red t. You thought that time was the same all around, but something tells us that that's not the case. What tells us that that's not the case? Well, x, the change in x. Okay, let's go back and think about the light pulses. Here's the light pulse. Now, let's consider another scenario. This was one scenario where the whole thing was moving at a certain velocity, and we were looking at these from an outside perspective. Now, let's look at another situation where the green one is moving in the left direction. Here's the green moving in the left direction. And the red is what we consider stationary. So let me kind of maybe make a little drawing here. Here's a light pulse. And we want to see how fast that light pulse, or how far that light pulse goes. How far the light pulse goes. So they both, this one's moving this way. This one we can consider stationary. And here's the red man. Let's go get the red man up there. The red man happens to be holding the flashlight. And the green man's perspective. And the green man's perspective is over here. And here comes the green man. As soon as the green man hits this point, the flashlight goes in that direction, and we want to know how far does that X thing get? How far does that go? Well, that's going to be velocity times time. But if it's light, then those two velocities have to be the same. And this is a very key point in all this. Very key point to try and figure this out. We're going to take this information and use it to figure out what this K value is. Now, if this seems like it's very confusing, it is very confusing. And that's why you might want to watch this part of the video several times. Wow. Getting really tricky now. This is where the math gets really crazy. Now, there's rules of algebra that say we can multiply the left-hand side together, and we can multiply the right-hand side together, and they're still equal. So, first of all, you have to convince yourself that that's the case. Then, here's the result. Here's the left-hand side multiplied together, and here's the right-hand side multiplied together. Here's a couple k's, kk, give me k squared. Here's these two expressions, x minus vt and x plus vt. And here they are down here. And now you have to know how to multiply binomials. So maybe that isn't something you really liked in school, but we've got to do it here to prove a point. So here's the x times the x. Here's the x times the vt. Here's the vt times the x, and that's a minus sign. And here's the vt times the vt. Now, keep in mind, the reds and the greens are separate. They're not the same. They're from different perspectives. So if we're ready, the next thing to do is to use these ideas. X, the green x equals speed of light times the green t. The red x equals the speed of light times the red t. So I can substitute those into this. Let's just do this one right here while I'm talking, and then I'll jump into it and get them all written here because it takes a long time for me to write. So what I'm going to do is take this x, and really I can make, really just to keep things clear, I can really put the red x here again. I'm not simplifying anything. And put the red x here. I said green x, now it's a red x. You can see what I'm doing on there. So this, all I did was just bring that down. Now, what I'm going to do is bring this whole thing down so we can fit it on the screen. Or let's see, do we have enough room? We can fit it in. Okay, anyway, uh, let me take replace the green x with the speed of light times t. If you buy that, here's the speed of light times the green t. And then that's multiplied times the speed of light times the red t. And that same thing is going to go in over here because we've got a red X and a green X. So it'll be a little bit different order there, but all that kind of stuff. So I'm going to substitute all of those in and come up with the final the expression here that we're headed for. So hang loose here a little bit and I'll get that drawn up. Okay, here's the setup here. I'm not sure how well you can see my setup, but here's all this stuff where I replace the x's. Now you might think, why do you replace the x's? Why replace the x's? Remember, our goal is to come up with these blue k's, the ones that equate all this stuff together. And that's where we can really come up with some good conclusions. So if we look at this, there are red T's and green T's on either side. So I can divide out green T and red T on both sides, and that gets rid of all the times here. Let's go ahead and let's see. Can I do that? Yeah, I can do that. Here we go. Get rid of that one. 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 And we're just making it simpler, which I love to make it simpler. It's much nicer to maybe we can come up with good conclusions rather than just a big mass of symbols. So what I'm going to do next is let's see if I can write this within a reasonable time frame. Okay, what do you think about that? Here's c squared, k squared. This is still in parentheses. So our k squared is kept all by itself. Now, if we can divide both sides by this expression, we should come up with something that we can use. Okay, I hope you can see my cursor. If not, I apologize for that. Anyway, let's take that top line. C squared equals K squared. This is what we carried over from the last whiteboard. And if we take out these two CVs, they cancel out. C squared over C squared minus V squared. And going fast here because we're kind of at the end of this video. Then that equaled K squared, just because that was left over. K squared equals 1 over 1 minus V squared over C squared. What I did was divide top and bottom by C squared. Then K, it was squared. Now we take the square root of all that. And I want to get quickly to this before I lose your attention, which you've probably already fallen asleep. Here's the X value. It used to just be X minus VT. Well, now it's X minus VT over this value, which if V squared is much smaller than the speed of light, what's this? That's pretty much just 1, because this pretty much is 0. So it's not going to make much difference until you get close to the speed of light, and then this is going to make some difference. So the X value is not going to be quite as easy as what we had before. Now, let's see what we got here. Okay, the time. The time is different. The time is different. This other green time is different than the red time. So this is where this relativity stuff comes in. Now, what's this factor here? Well, that factor is pretty much 0. So that's not going to be t is not going to be much, and this is going to be turn into pretty much 1. So it's just going to be t equals t until we get to velocities that are close to the speed of light. And that's where I want to end up.